Hi, today I want to deep dive into algorithmic paradigms. There are four main types of algorithmic paradigms: complete search, greedy algorithms, divide and conquer, and dynamic programming. Many algorithmic problems can be mapped into one of these categories, and the mastery of each one will make you a better coder. So here's an outline for today's deep dive. We'll start with complete search, and particularly the n-queens problem. Then we'll talk about greedy algorithms, such as fractional knapsack. We'll talk about divide and conquer and use binary search as an example. And then we'll dive into dynamic programming using binomial coefficients as the example. So complete search explores all possible candidate solutions. We can prune parts of the search space while backtracking, and common techniques are brute force, when we try every possibility, backtracking when we prune solutions that are not valid, and branch and bound when we prune infeasible solutions and branches that cannot beat the best solutions already found. Complete search can be used when the input size is small, or no efficient algorithm is known, or good opportunity for pruning the search space. Let's take a look at the n-queens problem. The problem is to place n-queens on an n-by-n chessboard so that no two queens attack each other by being in the same column, row, or diagonal. So for example, for n equal to 8, the most naive solution is 64 choose 8, and that leads to about 4 billion possibilities. If we place queens in different columns, that narrows down the choices to 17 million possibilities. And if we place queens in different rows and columns, that leads to 8 factorial, which is about 40k possibilities. We can represent a state space as queens at row equal to column. So for example, for a queens array below, we could see that there are 8 queens placed at 0, 0, 1, 4, 2, 7, 3, 5, and so on. So let's look at the n-queens pseudocode. So we have a search function that takes in queens and row as parameters. If row is equal to n, then we reached our goal state and we append a solution. Otherwise, we try every column in the current row. If the position of a queen is valid, we place the queen, and then we recursively search for the queens plus we add 1 to the row, right? So we recursively call the search function with row plus 1. After the recursive call completes, we remove our placement. So we set queens at row to -1. So essentially we are undoing or backtracking the placement of the queen. Let's talk about greedy algorithms. A greedy algorithm takes a locally optimum choice at each step with the hope of eventually reaching a globally optimum solution. So the key idea for greedy algorithms is to choose what looks best right now. We often rely on the greedy heuristics based on which we could sort and choose the best candidate. Some examples include coin change, minimum spanning tree, shortest paths, Huffman coding, and fractional knapsack. And we're going to take a look at a fractional knapsack. So the greedy knapsack problem is to select items to be placed in a knapsack of limited capacity W so as to maximize the total value of knapsack items, where each item has an associated weight and value. So we can define a greedy heuristic to be a ratio of the value to the weight of the item. And then we would like to greedily choose items that are high value and low weight at the same time and sort these items based on this criteria. And in the fractional knapsack, we're allowed to take fractions of an item as opposed to 0, 1 knapsack. So let's look at the pseudocode. At the beginning, we're defining our heuristic as the ratio of value to weight. Then we sort based on this heuristic, and then we update capacity and total value of the knapsack. Notice the time complexity here is n log n because of sorting. All right, divide and conquer is our next category. It's a technique that divides a problem into smaller, independent subproblems and then combines solutions to each of the subproblems. So the 3 steps of divide and conquer is to first split the problem into smaller parts, then solve the smaller parts, and then combine or merge solutions of the subproblems to get the final answer. And examples include merge sort, quick sort, and binary search, which we're going to look at next. Binary search is an efficient O log n algorithm used to find a target value in a sorted list or array. Instead of checking the elements one by one, binary search repeatedly divides the search space in half. So let's see it in pseudocode here. So in binary search takes in sorted array A and a target. Then we define left and right pointers. We compute in a loop a mid pointer. If A of mid is equal to target, then we just return the pointer. If target is greater than A mid, then we half the array. So we update the left pointer to be mid plus 1. Else, we update the right pointer to be mid minus 1. Otherwise, we return -1, which signals that no element was found. The time complexity of this division by 2 of our space is log n. And let's switch gears now and talk about dynamic programming. Dynamic programming is a technique that divides a problem into smaller, overlapping subproblems, computes a solution for each subproblem, and stores or saves the solution in a DP table to avoid recomputing it again. Key skills include defining the problem states and the relationship between the states, and then populating DP table in a top-down or bottom-up fashion. So in the top-down DP, the table is populated recursively, starting from the top and going down to smaller subproblems. In bottom-up DP, the table is populated iteratively, starting from the smallest subproblems and then building on and arriving at solutions to bigger subproblems. In both cases, if a subproblem was already encountered, its solution is simply looked up in the table as opposed to recomputing the solution from scratch, and this dramatically reduces computational cost. Some examples include Fibonacci numbers, 0-1 knapsack, all pairs shortest paths, and binomial coefficients. So let C of nk denote n choose k. Then we have our base case and recursion expression. And if we plug in n equal to 5 and k equal to 2, we get the recursion tree as follows. And notice there's entire subtrees that are identical in this recursion tree. For example, C3-1 is identical on the left and on the right. So we only need to compute it once, store the value in DP table, and then look up the solutions. And this is the core idea behind dynamic programming is memoization, or recalling the solutions to already computed problems. All right, so let's see our pseudocode for binomial DP. First, we create a table of size nk. Then we loop, and we fill in this table in a bottom-up fashion. The time complexity and space complexity are both O of nk. And now let's take a look at the code in the Python notebook. Here's our Python notebook. So we start with complete search and queens problem. We define a class. IsSafe method checks whether a queen can be safely placed without being attacked by any of the other queens. Then we have the search method, in which we do the backtracking. So essentially we start by checking if our final row is equal to n, in which case we append the solution. Otherwise we try every column in the current row, and if the placement is safe, then we update our queen's state space. We recurse and then undo the update or backtrack. Finally, we could solve by initiating the search from queens 0 and then print the board. And we could see that there are 92 total solutions found by backtracking. And the first solution is shown here. So you could see that no queen is attacking any other queen. Greedy algorithm, fractional knapsack. So we start by defining our heuristic, which is value divided by weight, and the comparison less than, which is self.cost less than other.cost. And then we initialize the item list. We sort the list based on our heuristic and pay the n-log n price here. Then we update capacity and total value of the fractional knapsack. And then we get, for this particular example, we get the maximum value of 240. Our next example is binary search. So here we define the left and right pointers and the algorithm. Notice that we sort our array here and we search for target 5, which is in the array. And then we do find it correctly at index 3. And finally, the dynamic programming example with binomial coefficients. We've got our top-down DP function, which constructs our memo array. And notice how we are storing values. If it's not equal to -1, we are returning the value stored in the table, right? And then binomial coefficient 2, which is the bottom-up DP, in which case we construct the table completely. And in this case, we're modeling our recursive relationship here. And also return, so for n equal to 5 and k equal to 2, we get the following table. Top-down DP only fills in the most useful to us in this example values, whereas the bottom-up DP fills in the whole table. And that's it. Hope you enjoyed this video. We covered 4 main algorithmic paradigms: complete search, greedy, divide and conquer, and dynamic programming. Being able to recognize and map a problem into one of these categories will make you a skilled coder. Let me know your favorite algorithm or problem in the comments description below, and don't forget to hit like and subscribe. Thanks for watching.